In this video, I want to show you some special cases that might occur while running the simplex algorithm. This is the second video on the simplex algorithm. So the first one, if you haven't seen that yet, gives you an introductory example to get an overview how the simplex method worked. In that example, everything went very smoothly. So here are a few things that might happen in general. So let's take a look at the following linear program. So we want to maximize x1. We have these inequalities. Of course, the first step is we want to have equational form. So to get this into equational form, we rewrite it like this with slack variables here and there. And if you don't know what equation form is, make sure to watch that video first. Now, from the equational form, we now can write a simplex tableau. For that, we need to decide on basis. But again, as in the introductory example, we can take x3 and x4, so our slack variables, as basis, because here we have positive values. So setting x1 and x2 to 0, I get x3 as 1, x4 as 2. It's a feasible solution. So we're going to take x3 and x4 as our basis, and then we get the simplex tableau where we have here the basis variables and write them in terms of the non-basic variables, and also the objective function we write in terms of the non-basic variables, which is simply x1 as you see here. As before, we see x1 shows up positively in the objective function, so we do a pivot on x1. We take a look at what constrains x1 most. Actually, only x3 constrains x1, so we're going to swap out x3, swap in x1, and as an exercise, you might simply write down the simplex tableau. I will now simply give it to you. This is the resulting simplex tableau. So here we have the simplex tableau, and again, we want to decide where to pivot next, or which variable to use to pivot next. Obviously, x2 shows you up positively, so we would do a pivot on x2. Now let's try that. We have to decide which variable to swap out. So we look at who constrains x2 the most. x1 does not constrain x2 because it shows up positively. x4 does not constrain x2 because x2 doesn't show up at all. Meaning x2 is actually not constrained. Which means that we can get arbitrary large solutions by increasing x2 as far as we want. So we're actually not going to do the pivot on x2. But what we're going to do is we keep this basis, x1 and x4. We keep x3 being 0. But now we take x2 as a variable which we increase arbitrarily. So we're going to write everything in terms of x2. So x1 is 1 plus x2, x2 is x2 itself, x3 is simply 0, x4 is, since x3 is 0, is 3. So we get the following way: 1 plus x2, which I read off here, setting this to 0, x2, which, okay, x2 is simply the variable we use, 0, because this is 0, 3, because this is 3 minus, and only x3 shows up here, and that is we set to 0. So we get this array, which is within my set of feasible solutions, where I can make x2 arbitrarily large equals 0, and the objective function is 1 plus x2. So now we can not only read off that our LP is unbounded, but we can also get a witness for that, or a set of solutions which give me arbitrary large objective value. So that was the first special case. The next special case are so-called degeneracies, and for that we're going to take a look at the following linear program, which of course we first write in equational form by using slack variables. Again, because we can use our slack variables as a basis, because here those values luckily are non-negative. This gives me the following simplex tableau. So I have my non-basic variables here, basic variables x1 and x2. I can rewrite everything in terms of those variables. Now I would like to do a pivot step, and I would do it on x2. Now if you take a look at who's constraining x2, it's actually x3 simply. So I'm going to swap in x2, swap out x3. This is this time actually quite easy. So I get x2 on this side equals x1 minus x3. x2 doesn't show up here. x2 shows up here. So I simply plug in what I had. So this is the simplex tableau. The only problem here being is if you look at the feasible solutions, is that we have before and after. So the feasible solution here I get by setting x2 and x1 to 0, and then x3 is 0 and x4 is 2. I get this basic feasible solution. And likewise here, if I set x1 and x3 to 0, then x2 is 0 again, x4 is again 2. So I have the same basic feasible solution. And we speak of a degeneracy here. In my drawing here, where I only have x1 and x2, it corresponds to this corner here, and because that's a 0, 0 on x1 and x2. And what happens here is that the simplex algorithm, at least for one step, gets stuck in that corner. Yeah, so I was here, I'm still here. Yeah, so we changed the basis, but we did not change the basic feasible solution. And you might wonder, can we get stuck here forever? In principle, yes, and that's called cycling. But by, in a clever way, deciding which variables to use to pivot, we can avoid cycling. So we were going to look at that in a later video. Here just the message: cycling or degeneracies occur. They could lead to cycling, but there are ways to prevent cycling. And you can also see the degeneracy in the figure here. So the reason we have a degeneracy here is because we have three. So if you look at the hyperplanes, we have the hyperplane here, we have this one here, and normally a corner would be defined by two hyperplanes. I mean, I have two lines, those give me a point. But here I have a third line passing through exactly that point. Yeah, so meaning that subsets of these two lines can define a basis here, and that's why this degeneracy occurs. So degeneracies are important, but we can handle them by appropriate pivot rules. And here actually in our example, if you now pivot, so next you would pivot on x1, and then you would actually reach the optimal solution, which is the solution up here. The last special case we're going to look at is infeasibility, more specifically infeasibility of the initial solution, the initial basis. So far we always were in the lucky situation that we had this linear program in this form, ax smaller equal b, and a non-negative b. Here we were always able to take the slack variables as basic variables, and in that way got an initial basic feasible solution. In general, this will not be possible, either because we do not have a program given in this form, or b actually has negative coefficients. So what can we do in that case? So here's an example. We have a linear program, and this is now in equational form, so we have no slack variables to work with. It is not clear how to pick our initial feasible solution. If you set all of these to 0, then you're outside of your set of feasible solutions, and we have to somehow find our initial basic feasible solution where we can start our LP. And for that we will solve an auxiliary linear program, and this auxiliary linear program will have auxiliary variables. We will have a plus x4 here, and we're going to have a plus x5 there. This, of course, doesn't seem to make any sense because we already had equality here. So what should be an x4 and x5 do here? So this will only work if we actually manage to set x4 and x5 to 0. And the following linear program will aim at exactly doing that. And this is now our auxiliary linear program. We have the program as we had it before, but now with our auxiliary variables here. And now we want to maximize minus x4 minus x5. If we manage to maximize this in a way that it becomes 0, then this is equivalent to our initial program. We have it here, that this actually has a feasible solution. But not only do we get this equivalence, but by solving the linear program up here, we will get such a feasible solution, which we can then use to solve our actual linear program. So let's try this by example here. So this is the simplex tableau that we now get by using our auxiliary variables as basic variables. But not only do we get the equivalence, but also by solving the auxiliary linear program, we get a solution to that program. And if the objective value is 0, this gives us a starting basic feasible solution for the linear program that we actually want to solve. Why are we now actually a step further? So how does this help us? We can use x4, x5 as our basic variables. Again, we have to be slightly careful. So it is important that these values here, that b is non-negative. But now we can easily make b non-negative by, let's assume there would have been a -4 here, then we can simply multiply that constraint with -1 and make sure that b is positive, and then only put in the auxiliary variables. We here have a simplex tableau with x4, x5 as basic variables expressed in terms of the other variables, so everything up to x3. Also z we can write now in terms of the other variables, and that simply by plugging in those two here, that gives me my z value. Now I want to pivot. I can pivot either on x1, x2 or x3. All of those show up positively. Let's say we pivot on x1. Then pivoting on x1, we look at who constrains x1 the most. x4 constrains it by 4. x5 constrains it not at all. So we're going to swap out x4 for x1. And then we get the following simplex tableau. And here we still can increase z by increasing x2 or x3. Yeah, so let's say we pivot on x3. Again, it's always a good exercise to write down the simplex tableau yourself. So do that, maybe. Okay, now I can show it to you. This is what you would get. And what we have now here is that z is -x4 minus x5. Now we achieved what we wanted to achieve. Both of the initial basic variables, which were our auxiliary variables, are now in the non-basic variables, so we can simply set them to 0 and we have a solution. So the solution here to our auxiliary problem, the optimal solution is 2, 0, 2, 0, 0. And this now gives me a basic feasible solution to my initial LP, namely simply the 2, 0, 2. And now we can go back to our initial linear program. This is our initial linear program, but we have a basic feasible solution, namely 2, 0, 2. x1 and x3 are the basic variables here, x2 the non-basic variable. This is what we get as our simplex tableau. Now again, x2 shows up positively here in z, so we're going to swap it in. We have to decide, do we swap it with x3 or x1? We take the one that constrains it the most, that would be x3. So then what we get is the following simplex tableau. x1 is, so it was 2 minus x2. Instead, if we now plug in what we get here for x2, then we get instead 1 plus 1 half x3. Likewise, x2, that's more easily seen. x2, if I bring it here, is 2 divided by 2, 1, and then minus 1 half x3. That has the following form. Now all the non-basic variables show up negatively in the objective function, so we know we have an optimal solution, and the optimal solution, so we set x3 to 0, and then we get 1, 1, 0 as optimal solution with an objective value of 3.